In January 2015, the first State of the Bay Research Symposium was held at the Alaska Ferry Terminal on Bellingham Bay. The purpose of the all-day event was to enhance communication and coordination between various agencies, organizations, and citizens involved in the protection of Bellingham Bay. The symposium brought together researchers, managers, and interested citizens who are all connected to the future of the bay. The symposium featured 7 distinct topics, including Bellingham Bay Yesterday and Today, local key issues, challenges, and research needs, physical processes, chemistry and water quality, biological ecosystems, regional research perspectives, and moving forward with limited funding. We will present the State of the Bay Symposium in 7 parts. This is Part 4, Chemistry and Water Quality.
Oh, beautiful, the suspense. So welcome to the session, Chemistry and Water Quality in Bellingham Bay. So this session gives an overview of sediment and water quality conditions and the implication for biological systems, and we're going to hear in a session about that following this one. And we have 3 speakers, and they will highlight current research results and also knowledge gaps and data gaps that we have. I'm Christopher Krems, and I'm sort of the head of the Marine Monitoring Unit, and I would like to sort of set the stage and ease you after your lunch into sort of Bellingham Bay again. So this is an aerial photograph flying into Bellingham Bay. This is a map where this picture was taken, Samish Bay. We find very interesting features already flying over it. This is sort of a ribbon of very sediment-rich water. We heard about it this morning. There's a frontal system, so the surface is not just homogeneous, but it's actually patchy and quite complex. In sort of the southern Bellingham Bay, Samish Bay region, we see a lot of organic debris mats. They're huge, like several sizes of blocks long. And we see a lot of sort of red-brown blooms in the southern portions. And just to give you an idea, when you sort of look onto northward, Lummi Island, you have sort of really sort of phytoplankton-rich water in the bay that can have all colors of green to red-brown. And then here you see sort of the first river plumes of the Nooksack River sort of coming around this point. On the left side, this is water from Rosario Strait. Just visually giving you already an idea how different Bellingham Bay is in terms of the algae response. Bellingham Bay has a lot of freshwater input and it's stratified. And because of the stratification, you can have internal waves at the density interfaces at depth, and they can interact with the surface. So you see these very nice features occurring at the surface. But the point that I want to make is the stratification, and you don't only have stratification, you have a lot of suspended sediment in the water. That also means that in terms of optical depth or where you receive light, you have a very thin layer, particularly towards the north, and that also affects how much phytoplankton can respond to higher nutrients. So towards the Nooksack River here, Portage Bay in the back, we're sort of right here, you tend to have almost no light, 1 or 2 meters down in the water column. Whereas when you go to the sort of southern end, you can have a lot of algae blooms that respond. Okay, as we all are familiar with, we have hypoxic water typically covering substantial portions of the bay, and this is a graphic from Jude Apple and his collaborators, and we sort of see long-term trends in the oxygen concentration, in particular in this region that has sort of the lowest residence time, or the largest residence time in the system. So you have a combination of factors. You have the stratification that impedes sort of the reoxygenation from the atmosphere because it's serving as a lid. You have very low residence time, and that draws down the oxygen. So that has a big impact on water quality, and you're going to hear about that in the next session. What I would like to do is sort of put Bellingham Bay, however, sort of into the perspective of what's going on Puget Sound and also what's going on in terms of oceanic influences. So we do long-term monitoring in Puget Sound. We have these stations sort of in mid-water bodies to look at ambient conditions, so we try to get away from sources. We fly to these stations once per month with a float plane and lower sort of a sensor package throughout the entire water column. And we measure a suite of physical, chemical, and bio-optical variables to look at long-term trends in water quality in context of estuarine circulation, in context of climatic variability, and also oceanic influences. And we also have, en route ferry monitoring systems in place and combine that with satellite images. But the strength of the long-term monitoring unit is that it has a long data set. It goes back to 1973, but we have very consistent data from 1999 onward. So at each station within Puget Sound, we kind of know what to expect at each time of the year. And this is very important because Puget Sound is highly variable in time and space. And in order to compare what's going on a larger scale, we need to somehow sort of find a mold that fits them all. And so what we do is we basically subtract the expected seasonality at each station from the observation. So we arrive at an anomaly. And why am I telling you that? Because in that way you can convey a lot of information very fast. An example here is the thermal energy content in the depth 0 to 50 meters. So that's kind of the heat in the water column. And the point that I would like to make is that the ocean has a very strong influence on a lot of physical properties in Puget Sound. So each little pixel is a sampling event. We have 12 per year. Each line represents a station of our entire long-term monitoring station network, and this is over time. And you see sort of color. Red means higher than expected, green lower than expected, black would mean sort of expected values, and gray are sort of the data gaps where we couldn't fly, and so it's also a performance measure how often we actually made it into the field. So when you look at that, you see already that there are big trends that go through the entire system by the big shifts from green to red, sort of in the middle of the last decade, etc. So this whole network is responding to large-scale drivers as well, and you need to understand these in order to understand also water quality and sort of more local measurements. Okay, so when you basically take an average over all these anomalies for the entire year and the entire station network and plot that against an oceanic index, the Pacific Decadal Oscillation, which is the anomalies in sea surface temperature, you see that the two are very closely following each other or are related. So basically, the surface water 0 to 50 meters very closely responds to the ocean in Puget Sound. When you look at oxygen, and oxygen is an important water quality parameter, we can do a similar thing. And we basically look at the oxygen deficit. And we do that. So what is the oxygen deficit? The oxygen deficit is basically the amount of oxygen that you would need to put into the water in order to reach saturation. Yeah, and so you can do that over a certain thickness of the water column, and we do that 20 meters all the way to the bottom. So a high oxygen deficit means that oxygen concentrations are low, and vice versa. So when you play the same exercise again, here we have data from 2002 onward to full depth, and take sort of a yearly Puget Sound-wide average, we see sort of a curve here in red, and underneath it I put the anomalies in the upwelling index. So upwelling brings low oxygen water at the coast, closer to the surface so it can move into Puget Sound. So these are very closely related. So think of Puget Sound at the surface, and at depth the ocean has a huge impact. And let's say this is the ocean. So it's the gorilla in the equation. But there's something else going on in the system. So not everything is okay, and we can blame everything on the ocean. When we look at the nitrate concentration in the surface water, 0 to 30 meters, again, sort of in that anomaly space, and look at the year-to-year variations, we see a significant increase in nitrate in the entire Puget Sound region. And the same holds true for phosphate. And so our common understanding is, if you increase nutrients, macronutrients, you promote more algae growth, right? That's sort of the textbook that we all understand. Well, something is happening in the system that not only sort of nitrate is increasing, but the balance of nutrients are shifting. And an important ratio is the silicate to nitrogen ratio. It's sort of a putative ratio that can indicate whether you had anthropogenic or human inputs into the system, because we add nitrogen disproportionately higher than silicate. So this has been in the literature sort of a putative indicator for human inputs. And the ratio has been significantly declining, much more so, 2 orders of magnitude more so than in the ocean of the coast. And why is that also important? Because silicate is very important for diatoms to grow. And by shifting nutrient ratios, you can shift species composition and change the entire food web of the system potentially. So silicate is used by diatoms. If you have less silicate because the ratio is plummeting, you give a lot of opportunistic species that don't require silicate a competitive advantage. And what comes in typically are sort of flagellates. And they tend to form huge blooms. This is Case Inlet 2 years ago. These are little boats, the little dots, just to put it into perspective. I mean, these are huge blooms that form right at the surface in red-brown colors. And why is that important? Because flagellates tend to be, in terms of food for copepods and fish, sort of less than optimal. A lot of them have sort of harmful algae bloom characteristics, and so that's not a desired species that you potentially want to have. Okay, so we can play the game and look at sort of 14 years of changes and do that for each station and extrapolate out when we would hit a putative ratio of 1:1. So if we do that, then there are some stations that definitely kind of fall out, and these are sort of indicated here in red, matching basically the years it would take to reach the 1:1 ratio. And what comes out are the typical sort of finger inlets of South Sound, Possession Sound, but also Bellingham Bay. So things are shifting potentially in the entire food web. Just to give you an idea what that looks like, in South Sound, this is a sort of dinoflagellate bloom in Totten Inlet, just taken this year. You also can have that in Bellingham Bay. This is north of Guaymas Island, sort of looking northward. You see these nice little red blooms occurring. So up to here, it kind of makes sense. Nutrients are increasing. You see more blooms we understand the system, but it's not true. When we take sort of the depth integrated chlorophyll in Puget Sound and look at it over time in anomaly space again, we see a significant decline in chlorophyll. So phytoplankton biomass is decreasing. And at the same time, transmissivity over the water column is increasing. So that's very consistent with the decrease in chlorophyll. And transmissivity is basically the clarity of the water. We also see a shift in the quality of nitrogen that is available. And we can express that as a ratio of nitrate to dissolved inorganic nitrogen. So that includes nitrate, nitrite, and ammonium. And so there's more nitrate out there. So the question is, maybe phytoplankton can take up the nutrients that we see out there. Maybe there is something going on in the food web that might be driving that. And why do we say that? Because we observe gigantic blooms of Noctiluca in Central Sound and also in other places up to the San Juan Islands. And this is sort of, this was taken, I think, 1 or 2 years ago. This is a sailboat, just for scale. This is Central Basin, this is Bainbridge Island. These blooms are huge, and when they're starved, they come to the surface. Here's an example. This is Noctiluca, just eating a diatom. And Noctiluca tends to feed on all kinds of stuff and really competes with copepods for food. It eats nauplii, it eats fecal pellets. It changes potentially the entire inner working and material cycling of the food web. If you're interested in that, we have a poster out there where we try to piece the lines of evidence together in order to promote more research in understanding that. And there are also cards if you want to have one of these, okay, with a scan code that gives you a talk about the subject. Okay, enough of that advertisement. So how does Bellingham Bay fit now into the bigger picture that we observe? Well, in Puget Sound, we saw the increase in nitrate. In Bellingham Bay, it's the increase in ammonium. That's very different. Where they are similar is the increase in phosphate, the shifting ratios in silicate to nitrogen that I showed you, and the water is getting clearer over the entire water column. So that's not necessarily inconsistent with all the sediment inputs from the Nooksack, because that looks just at the surface, but basically this is over the entire water column. Where Bellingham Bay is also different than Puget Sound is in basically its phytoplankton concentration. It hasn't really changed. It's extremely noisy, but there are no trends, no declines. And also the ratio of nitrate to DIN, giving you the quality of nitrogen, has not really changed. There's a lot of noise in it, though. And if you just want to sort of place it and rank it towards all our other stations, in absolute sense, the N to P ratio ranks amongst one of the highest with our stations, but the nutrients rank sort of with one of our lowest. So we have sort of 18 long-term monitoring stations, and they're really down there. So where are the nutrients? Maybe they have been already converted into biomass. That's a sort of a question that we can't really answer. But I would like to draw your attention to the concentrations of ammonium. And this is, again, in anomaly space. And you see that ammonium has really significantly increased. So in absolute values, if you average ammonium and compare to all the other stations, Bellingham Bay only ranks position 7. So the Sinclair Inlet and Dana Passage and Budd Inlet, they have higher concentrations. But when you look at the rate, it has the steepest rate in any of the stations that we have. So something is going on. We don't know what it is. Maybe it's tied to the rivers. We heard Marcus sort of alluding to that, and also Eric Grossman. But I think we would like to make that connection, what's going on in Bellingham Bay. And with that, I would like to set the stage to our first speaker here, Valerie Partridge, and you have that talk that you wanted to update last minute, one of these last minute things.
I apologize for the delay. Based on some of the information that I heard in this morning's session, I wanted to update my presentation. Someone in an early presentation made a remark about rapid turnover in staff, and I wanted to let you know that in the marine sediment monitoring component, we have some very long-term members. We love our jobs, and we're staying. Maggie Dutch, our team lead, Sandy Weekland has been there for more than 20 years. Both of them have been doing this for more than 20 years. I'm going on 14 years now. We've just hired 3 new people. One is our Washington Conservation Corps intern, Brooke McIntyre, and 2 new taxonomists. What I'm going to do today is basically 2 presentations. One is on the benthic invertebrates in Bellingham Bay and in perspective. The other is on sediment chemistry in Bellingham Bay and put in perspective. I'll give you a high-level overview of the sediment monitoring program to begin, and to end, I'll give some information from a regulatory perspective on behalf of someone in the regulatory program. The sediment monitoring component of the Puget Sound Ecosystem Monitoring Program has been going on since 1989. It's a status and trends program which looks at sediments with the sediment quality triad of sediment chemistry, sediment toxicity, and benthic invertebrate communities. And the purpose is to assess sediment condition. Well, we've been doing this long enough now, we can also measure trends as well as status. So there are several components to our monitoring program. The first is our 10 long-term stations, which have been sampled every year since 1989. We sample them annually for benthos and every 5 years for chemistry. These 10 stations were selected because they represent different types of habitats in the southern Salish Sea, and they have different types of benthic communities. And Bellingham Bay Station number 4 is one of them. We also have a regional monitoring program which has been going on since 1997. We established a baseline throughout the southern Salar Sea from surveys that were done from 1997 through 2003. We just finished our second full round of sampling the entire sound last year. We are regrouping this year, and we begin again our third round next year, and I'll get more into that in the future. So I will be discussing somewhat the Strait of Georgia region, which includes Bellingham Bay. It basically is all of the embayments from Boundary Bay down to Fidalgo Bay. The third component of our monitoring program that I'm going to discuss is our urban bays monitoring program. And this began with the Urban Waters Initiative in 2007. We began with Elliott Bay and Commencement Bay and gradually expanded that to 6 urban bays, of which Bellingham Bay is one. Since we've just finished our second full rotation through Puget Sound, we can also now revise the baseline for Puget Sound based on all of the newer information. This is the study area for the urban bay study in Bellingham Bay, and I wanted to show you this to indicate what we are and what we are not sampling. One thing that you'll notice is that we don't go very far towards the Nooksack Delta. And the reason for that is the limitation of the boat. We need to have 6 feet in order for the boat to get in there. The definition of the survey area is historically defined based on the survey that was done by jointly with NOAA in 1997 through 1999. So that's why we have both the study area that we do and the particular stations that we have studied. All 30 of these stations were sampled in 2010, but as part of regional sampling in 1997 and 2006, some of them were sampled in those earlier times, and I'll be getting into that. Finally, our long-term station 4, which I alluded to before, is located not in the same area but nearby. As I mentioned before, we use the sediment quality triad of chemistry, toxicity, and benthos to evaluate sediment quality. We've been looking at over 150 chemicals every year for the last several decades, and from the concentration information for 41 chemicals for which there are state sediment management standards, we have derived a chemistry index. We rely on 2 toxicity tests. One is the amphipod survival test. The other is the sea urchin fertilization test to give us information on effects of the sediment and the pore water, respectively, on benthic invertebrates. And the results of those go into our toxicity index. Finally, for the benthos, we identify to as low a level as possible, species if possible, all of the organisms which we capture in a sediment grab. And from that information, we derive a number of different indices of community and diversity. We also look at the presence, absence, and abundance of sensitive taxa, tolerant taxa, and invasive species, and combine all of that information into a benthic index. The benthic index, at this point, what we've been using recently, just defines benthic communities as being either unaffected or adversely affected by stressors. And we're not making a distinction between anthropogenic and natural stressors. These 3 indices then are combined into the sediment quality triad index. By the way, both the chemistry index and the sediment quality triad index were adopted by the Puget Sound Partnership and used as has some of the indicators on their website for characterizing Puget Sound. I mentioned the benthic index as being a two-state index. Either communities are indicated as being unaffected by stressors or adversely affected by stressors. And we were quite concerned when we calculated the numbers and determined that every single one of the samples that was collected in 2010 had characteristics of adversely affected communities. And this alarmed us greatly. It was the only urban bay in which this was found. So we wanted to explore that further, obviously. In comparison with the 5 other urban bays, you can see that the other urban bays have varying degrees of percent of area with unaffected versus adversely affected communities, and that as we resample those bays on a 6-year schedule, that we can see changes over time in the community health in those bays. So let's take a look back then at the times that we sampled for regional surveys where samples happened to land in Bellingham Bay. And the first thing we notice is that in 2006, every single one of the communities sampled was adversely affected. If we look back to 1997, that was not the case. So it makes us wonder what happened between 1997 and 2006. This is another way of viewing the same thing. This is a non-metric multidimensional scaling map. What you're looking for here is how close or how far apart the points are. This takes information on all of the species, which may be dozens or hundreds in numbers, all of the species, all of the abundances in each of the samples, and simultaneously calculates how similar or dissimilar those samples are. And what we see is that the 2010 and 2006 samples are similar to each other. By the way, there's no directionality on this map. All you're looking for is closeness or distance. So the closer together the points are on the map, the more similar these communities are. The farther apart they are, the more dissimilar they are. You also see that there is quite a distinction between the samples that were collected in 1997 versus those in 2006 and 2010. So there's been quite a shift from 97 to 2006 and 2010. Furthermore, we see that a couple of the points which were resampled showed significant changes, and in particular, that one. That's why I wanted to modify my presentation after hearing what Eric had to say this morning. That sample was collected at our station, which is closest to the Nooksack Delta. So it makes you wonder if that sample was buried, if that station was buried. The community was very depauperate in terms of the abundance and diversity of the species. And the species were very different, completely different species mix from all of the others over all of the years. So we have speculated about a number of different possible mechanisms. I'm not going to go into this, but just to let you know, there are a number of different avenues that we're looking into that might explain these trends that we're seeing not only in Bellingham Bay. This is definitely the worst case scenario, but we have been seeing declines in abundance and taxa richness in region after region and bay after bay throughout the southern Salish Sea, which has us concerned. Now let's take a look at our Station 4. This we have sampled every year since 1989, And there are several points that I want to make here. The first is that in 2013, the number of polychaetes basically doubled. And that is almost entirely due to a stress-tolerant polychaete called Apheliceta, which is definitely associated with conditions of high organic load. The other thing to notice, which is probably even more obvious, is what happened in 2014. And that's almost entirely due to a newcomer, something that we have not experienced before in this type of numbers. And this is actually photographs of our sampling last year at Station 4, where we had hundreds of these polychaetes, which are big, fat, but short red worms called Scalabregma californicum. And our estimates, because we haven't gotten the numbers back from the taxonomists yet, our estimates of the abundance of Scalabregma in 2014 is higher than the total number of critters in all of the earlier years. Something is going on, and we don't understand this. We can also look at patterns in what we call functional feeding guilds. Functional feeding guilds were defined for Salish sea benthos by our Canadian colleagues who did all the work of literature reviews and looking at mouth parts under the microscope and so forth, and decided and designated characteristics of the benthos which integrate where they live, how they live, what they eat, and how they eat it. So we have different categories of functional feeding guilds, including benthic carnivores, surface deposit feeders, subsurface deposit feeders, and a few others. And if we look at this, we can see that there's a very regular pattern, basically a 5-year cycle in abundance in a number of these organisms when you look at it by feeding guild, although the cycles seem to be getting shorter in the later years. This is not taking into account 2014. It does take into account the increase in Apheliceta seen in 2013, but if we were to add in what we saw in 2014, it would be off the chart. And that is just in the subsurface deposit feeders. That's Scalabregma, among others, but that increase is in Scalabregma. Another thing that we've noticed is that the species have changed over time. So the species which are abundant are different now and have changed over the years. And there's another way we can look at this. This is a standard cluster analysis, again looking at the similarity of the communities. This is just within Bellingham Bay, just within Station 4. And if we translate these groups in the cluster analysis and express it on an MDS map, what we see is this. If you trace beginning from 1989 at the beginning of the arrow to the end at 2013, what you can see is that there is change over time in the benthic communities, and that furthermore there seem to be clusters of years together which are more similar to each other than others, but definite shifts in the benthos, changing with time at Station 4. So summarizing the benthos results for Bellingham Bay and in comparison, one thing that I didn't mention was that we have seen very little correlation, basically no correlation whatsoever, with the sediment contaminants, but I'll get into that further. We have seen changes over time in the benthic communities. We do have evidence of some natural cycles, but we do also have unexplained species appearances and disappearances. Where we have gaps then are in our knowledge and understanding of life histories. For example, nobody knows very much about Scalabregma at all other than its taxonomy. We don't have much knowledge of the trophic webs, about the interconnection between the bacterial level, the microbial level, and on up to the higher levels, and the interconnections. So those are things that we need to look into. Challenges, we can't do everything, but we're also concerned with sampling these 10 fixed stations over time that we might also be affecting what we're seeing. Opportunities there are for program revision, and I'll get into that in a minute. Now, going back to this, I said I was basically doing 2 talks, one on the benthos and one on the chemistry. So here's a very awkward segue into the chemistry. As I mentioned before, we have sampled over the past 20-odd years over 150 different chemicals, some of them consistently over all of the time, others have been added or dropped. And some of them are ones which are represented by state sediment quality standards, sediment management standards. One thing to note here, though, is that we detect metals and PAHs almost everywhere and very little else. We're doing an ambient monitoring program. We're looking at the most recently deposited sediments, and that's important. Just giving a picture of mercury and low and high molecular weight PAHs in Bellingham Bay with respect to the rest of the Strait of Georgia region, and the results are about what you would expect, that in the more industrialized areas, the concentrations are higher. Towards anacortes, the PAHs are higher. There's a high result for mercury in Boundary Bay, and we're not quite sure why. Comparison to sediment management standards, well, as I mentioned, for the most part, we're not even detecting most of the chemicals that they're concerned about other than the metals and PAHs, and those concentrations tend to be low and not exceeding the sediment management standards in Bellingham Bay or in Puget Sound as a whole. And where we do see exceedances of the sediment management standards, it's in places where you'd expect, in the highly urbanized and industrialized areas, Elliott Bay, Commencement Bay, Sinclair Inlet. This is how the chemistry index played out in our samples in 2010. And in comparison with the Strait of Georgia and all of Puget Sound now, we can see that there is a slightly larger percentage of area in Bellingham Bay with low exposure to chemicals as opposed to minimum exposure compared to the Strait of Georgia region as a whole and Puget Sound. We can also look at these comparisons for the different urban bays, and again, the results are about as you would expect. We can also see that there have been some improvements in the contaminant quality over the different years. In Bellingham Bay in 2010, we also had the opportunity to do a focus study on personal care products, pharmaceuticals, and perfluoroalkyl substances, or PFASs. Pardon?
What is that?
Oh, glad you asked. Of course, the pharmaceuticals and personal care products are what we use every day. The perfluorinated chemicals are in non-stick products. They're in firefighting foams and the like. They have nasty effects on aquatic critters. And there are basically 3 which are found almost everywhere. So first is trichlorocarban, which is the active ingredient in hand sanitizer. We find that just about everywhere. Diphenhydramine, an antihistamine, so basically your Benadryl, and a diuretic. These are the three pharmaceuticals that we tend, or personal care products that we tend to find everywhere. Not very many other of the 119 chemicals that we tested for were found. And of the perfluoroalkyl substances, only a few showed up. The one which showed up more often is a substance with the acronym PFOS. It was found in higher concentrations in Bellingham Bay than other places. So in summary for the chemistry, as I mentioned before, we detect the metals and PAHs just about everywhere, but find very little else. And we do the standard suite of pesticides, PCBs, PBDEs, other organics, and we basically are not able to find them. Now, we don't know whether that's a methods issue or just that the sediments are that clean. Few concentrations exceed the sediment management standards, except in urbanized and industrialized areas. As I mentioned before, we are looking at the most recently deposited sediments. We're looking at the top 2 to 3 centimeters. And we found only a few of the over 100 PPCPs that we looked for, but we did find them, including 200 meters down, which surprised everybody. And finally, the chemical signatures do vary by region and bay. There are lots of other chemicals out there that we just don't have the money or the methods or the labs to be able to detect. And so one of our challenges then is to be able to get beyond just the what I call legacy chemicals that were the focus of the Superfund programs from the 1980s, the heavy metals, the PCBs, PAHs, and move on to the newer chemicals that we know are causing concern. But we don't have unlimited dollars. However, we have the opportunity of our program revision. So we are in between our last round of sampling and before starting our next round of sampling, we are meeting with a number of stakeholders with respect to revising our program, revising the chemistry list that we look at. So we'll probably be dropping things like the pesticides and maybe just looking at PCBs only in areas where they're historically known to be found. Our toxicity tests, we will be looking at revising the quote-unquote gold standard of the amphipod survival test has actually not been sensitive enough for Puget Sound. It's more an indicator that's useful in heavily polluted areas such as Chesapeake Bay or New York Harbor. And finally, with respect to our benthos, we are in the process of developing a multimetric benthic indicator with help from our folks at the Southern California Coastal Water Research Project, looking at possible traits-based indicators, so building on the type of information such as in the functional feeding guilds, and also collaborating with other researchers to look at benthic changes in relation to other food web changes in Puget Sound, such as Christopher alluded to. Just a few slides from Lucy McInerney of the Toxics Cleanup Program in the Northwest Regional Office of Ecology. What I've been referring to with respect to the sediment monitoring that we do has been ambient monitoring of the most recently deposited sediments, but that's not the definition that's used for regulatory purposes. For regulatory purposes, the Department of Ecology looks at known or suspected hotspots. They look at the entire biologically active zone, which in Bellingham Bay is the top 12 centimeters of sediment. And so they're looking at older sediments, which tend to have higher concentrations. You've seen this slide a number of times. A poster of this is out for your review. And finally, for more information, the Toxics Cleanup Program does have a website which has up-to-date information, and you can also sign up on the sheet out there to receive updates. Thank you. Oops. Okay.
So I'm switching a little bit back to bacteria. I'm Jean Snyder. I am a public health advisor for the Washington State Department of Health, and I work in the Office of Shellfish and Water Protection. And our primary goal is to protect public health. And our growing area section, which is the section I work in, our primary goal is to make sure that shellfish that's harvested throughout Washington is safe for you to eat, both in your restaurant and on if you just go out and harvest it yourself. And so today I'm kind of going to step through an overview of the kind of shellfish growing area monitoring we do, which includes bacteria sampling. And then I'm going to give, using our new commercial shellfish map viewer, I'm going to give you a short tutorial on that, and then how it also is a great segue to visually see how fecal coliform is looking in Bellingham Bay, and specifically Portage Bay. So, for those of you who don't know much about the shellfish world and what Department of Health does, we manage and classify all marine areas throughout Puget Sound and the Pacific coast so that shellfish can be commercially sold and recreationally harvested in these different areas. We have about 102 commercial growing areas throughout Washington. And I'm not going to go through how we do our initial classification, but let's say when we get to the point and classify growing areas, they can be classified as approved, so they can be open to harvest at any point in time. They can be conditionally approved. You can kind of see the little yellow square in Drayton Harbor, that's conditionally approved. So there's times when the bacteria levels are really low, but there are still other times when bacteria levels are high. And then there are prohibited areas, which are kind of the red areas. And there's a known pollutant there that is impacting that water body, and it isn't safe for shellfish to eat shellfish from that area. And so in Whatcom County, there are 7 growing areas: Drayton Harbor, Birch Bay, Alden Banks, which is a gooey duck harvest area, Lummi Bay, Lummi Island, Eliza Island, which is another gooey duck harvest area, and then Portage Bay, which is the largest growing area outside of Samish Bay in southern Bellingham Bay, in the northern Bellingham Bay watershed or area. So what do we do to kind of make sure, once we make this initial classification, to make sure that water quality and pollution sources aren't impacting these marine areas? Well, one of the things which most of you are probably familiar with is our marine water monitoring program. We have over 1,700 marine stations throughout Washington waters that help us classify growing areas for shellfish harvest. And we sample at a minimum of 6 times a year. Some we sample more frequently. We sample for fecal coliform, salinity, water temperature, and then we note what the tide condition is, whether it's ebb or flood. And similar to Gary's talk earlier, we monitor fecal coliform because it's an indicator bacteria of things that could make you sick, such as norovirus, other bacterias, and contaminants. And so to monitor these water stations, we have to have a minimum of 30 samples to be able to classify the area. And this is from our national standards. So the National Shellfish Sanitation Program Standards, which we administer from the FDA, has a fecal coliform water quality standard. And it has two parts of the standard, similar to what fresh water quality standards are that the State Department of Ecology has. And so we have a geometric mean of, those 30 samples have to have a geometric mean of less than or equal to 14 fecal coliforms per 100 milliliters, and an estimated 90th percentile of less than or equal to 43 fecal coliforms per 100 milliliters. And if that isn't happening, then we have to evaluate where the potential pollution sources are and that it may not be safe, and we may have to change the classification of a growing area. The other thing we do less frequently is we evaluate the shoreline. We do what's called a shoreline survey, and we use some local information from different either state agencies, local jurisdictions, whether it's health department, public works, tribes, and we look at water quality and shoreline drainages. We look at potential bacteria sources from wildlife, agricultural, on-site septic systems, marinas, and wastewater treatment plants. And those are typically done every 8 to 10 years. And there are always ongoing shoreline surveys throughout Washington. So it may not be done, the most recent one in Portage Bay was done in 2009. And so the next step I'm going to take you to is a lot of this information we have now moved into a new database, which we've been working on for the last 2 years, and now has culminated into a new commercial shellfish map viewer that you're able to pull down this summary information of all the 1,700 marine stations in the state of Washington, and also identifies why those red areas are prohibited. It gives you kind of a general information that we're collecting as our office. And so bear with me, we're gonna go to the internet. So this is live, and it's updated as our database is updated. This is a screen when you first go to it that you're gonna see. And I know a lot of you have probably seen our new recreational shellfish safety map. This is similar to it, but it provides more information. It's an ArcGIS-based mapping platform. So similar to if you guys have used ArcGIS, you can turn on and off layers. You can select information and make tables from it. You can make your own maps from it. It's a great tool that we have found that both stakeholders are excited to use and our commercial shellfish growers. And so this is just a splash page. When you first pull up, it's similar to a map. It's got a legend, and the only thing that the legend will they'll show in the legend is what layers you have turned on. So originally when you come here, the only thing that's turned on is closed parcels, and then if we drag down here, all the different classifications that we have. And so you can kind of see that growing areas stretch from down in Willapa Bay all the way up to the Straits, and there's a lot of different shellfish areas in Washington. And so if we kind of zoom in closer to North Sound, in Bellingham Bay, it gives you kind of the similar map that I showed you on the previous slide. It gives you all the growing areas. Well, to give you an indication of the different types of data that we have in this, that we're collecting and that are in our database, that are continually updating you can see the very top one is all of our marine stations in Washington. So if we turn that on, just looking, if we zoom out a little bit, just looking all those dots are different marine stations that we're sampling at least 6 times a year, which is a great logistical feat for our water quality sampling staff. Zoom back over, down to Bellingham Bay. And so more specifically, if we go to, I turned off the commercial growing areas. But here you can see the other type of information that you can turn on and off. We have commercial shellfish harvest sites. We also do have some recreational information on there. We have the locations of all the recreational beaches and whether they're open or closed for safety, for health reasons. We also have biotoxin closures, closed parcels, county parcels, county lines, and a variety of different information here. But the great thing is here we can see what water quality is actually looking like in Portage Bay. So this is a Portage Bay growing area. If we click this identify tool, it'll tell us why this red polygon is prohibited. Well, it's prohibited because there's a wastewater treatment plant outfall there. And you can do a similar thing. You can select another polygon. You can select a marine station. And then it gives you the sampling information, basically the summary information. So it gives you the geometric mean, the 90th estimated 90th percentile, whether it's meeting the NSSP water quality standards, and then kind of the range of the results. And it also gives you the latitude and longitude. And my favorite tool on here is not just the identify tool, but is this search tool, because this is a great way to pull all of that summary marine data into a table format and export it into a table. And so if we use a polygon, change our search layer to water quality sampling stations, move this out of the way, select our polygon. For all the marine stations in Portage Bay, it brings it up in this similar kind of table format, but you can see there's kind of two different tables on the top. This green one in the search function turns it into an Excel table, and that can be exported. And here it gives us all the marine, all the summary marine water or fecal coliform data for all the stations in the area you selected. And it also tells you the most recent sample date and when that was entered into our database. It isn't the most recent taken, it's what's been uploaded into our database. And so clicking on this export tool, you can then export it into a CSV, which you can use in an Excel table and pull data throughout Puget Sound on this. So we're going to click clear. But as you can see, if we turn back on the legend, these red dots are saying that this portion, similar to what Gary was talking to earlier, is that there's a portion of Portage Bay that is not meeting water quality standards. And that portion you can see is by those 5 stations that are failing. They have estimated 90th percentiles greater than 43. And so right now we are working in conjunction with the Lummi Nation to downgrade a portion of Portage Bay because it's not meeting the standards, and during certain periods of the time it is not safe to eat shellfish harvested from there. And similar to what we've talked about earlier is that there are potential pollution sources coming from throughout Whatcom County. And I guess kind of the greatest need, if we're going to talk about greatest needs from our department, is we have limited staff and limited resources to collect these 1,700 marine stations. We really want to encourage people to use this data, to use this information, whether it's writing grant reports to show the work that the state agencies are doing, whether it's gathering data, gathering information, and identifying what water quality looks like throughout Puget Sound. And to continue doing water quality and bacteria sampling outside of a regulatory arena. And so kind of to go back to this gives you, this link will take you to the recreational shellfish map. This takes you to our home website. We post all of our preliminary raw data sheets at this website. And then we also team with the beach program, who monitors enterococcus on the beaches, two in Bellingham Bay, one at Little Squalicum Creek, and they also have at Marine Park, I believe. And so if you had any questions or wanted information about recreational contact with water, please go to the beach program. And we're continually updating and revising our mapping feature. So if you see something that's incorrect or information that's inaccurate, or you would like to see information that you think our office is collecting on this website to make it easy accessible, please contact me with any further questions. I'm kind of the main point of contact when it comes to our database and our mapping. Thank you.
Thank you very much, Jean. So our next speaker is Brandy Lubliner. Yes, I forgot that. This is stage fright, I think.
Hi, I'm Brandy Lubliner. I only work with Christopher at Ecology.
We see each other every day. That's embarrassing.
I'm really happy to be here. Sue, who just stepped out, gave me a call and wondered if Ecology had anything they could say about stormwater. And actually, it's very timely because we actually can finally say something about stormwater. And that's because Ecology issues the stormwater permits to Phase 1 and Phase 2 communities, and I don't really have a sense of if you guys understand what Phase 1 and Phase 2 are. Phase 1 communities are the largest communities, like Seattle, Tacoma, Snohomish County, King County, Pierce County. And the Phase 2 communities are the smaller communities all the way down to about, I think Alcona is our smallest Phase 2, so we can get pretty small. But we issue our municipal stormwater permits, and they're very large permits. They have a lot going on in them, and they have a lot of requirements in them. And one of the requirements is for monitoring. And Ecology issued its very first stormwater permit in 1997, and we didn't have any local information. We were relying primarily on national studies, the NURB, National Urban Runoff Program. And we didn't know what that data, is applicable to us. So when we reissued the 2007 permit, we required monitoring. And so this talk is largely about the data that was collected in the 2007 to 2012 permit, and that permit required monitoring only of those largest communities. So that's what this talk is going to be about. And I have co-authors that have brains much better than mine for statistics and programming, and you'll see why that'll become very important soon. So I will give you a teaser about monitoring in the new permit at the very, very end of the talk. Okay, the purpose, as I was alluding to, was that we needed to gather a data set about stormwater from our region. And we wanted to basically get a status assessment. And then at some point, look at outfall data again and begin to have a trends assessment. But this first bit was definitely for status. And we asked the permittees to characterize stormwater concentrations from outfalls by certain land uses. And we gave them 4 options, and the cities and counties had to monitor 3 of the land uses, and the ports had to monitor 1 of the land uses. And that way we could begin to understand what runoff quality was like from various intensities, like how we use the land. And you can see the Phase 1 permittees here. The ports were co-permittees. The 2007 permit laid out the strategy for doing this monitoring so that all 8 of these communities were collecting data the same way so that we could compile it later. And it was very specific. We wanted, there was a lower threshold on the storm, like the rainfall amount. We wanted at least 0.2 inches per hour to be considered a storm event. We wanted 6 hours of dry period between storm events, so you knew when to stop monitoring and when to start again. We wanted them to collect 11 storms a year, and they collected storm event data for 3 years total out of the 5-year permit cycle. We wanted them to collect these data using compositors because we want it to represent this storm event, not just a grab sample. You know, fecal you can't send through a compositor, or total petroleum hydrocarbon, you don't send through a compositor. Those have to be grab samples. But for the most part, we really wanted the sample we sent to the lab to represent 75% of the hydrograph. And then we asked for the bulk of the sampling to be in the wet season, and some dry season storms, if we get them even around here. So we laid out a lot of those requirements. We actually did also put in the permit a sediment requirement, and it was just a single annual sample, but we wanted it to be in line in the pipe system, and you could collect it by mounting a bottle upright, and just every time the water level went over the mouth of the bottle, you know, sediment would fall in and eventually displace the water. And that would just collect it all year. Or some phase ones just did a single grab at a place where it would accumulate over the year. That program wasn't as designed in the permit, so there was more flexibility. And they monitored for a very wide variety of contaminants. That's because we really didn't have any regional understanding of what our stormwater's like. And so we asked for conventionals and some physical parameters like turbidity and TSS, nutrients. MBAS is a surfactant. Nutrients, total and dissolved, some metals and organics, some pesticides, and then petroleum products. And in the sediments, largely the same suite. Okay, so I'm just going to kind of jump into results. So actually, before I jump into results, I'll just say the timing on this is really wonderful because the permit cycle is a 5-year cycle. They were given 3 years to monitor, and we just got the last of this data set in about a year ago, and so we've had about a year and a half to begin to analyze this data set. And this data set is huge. There's 600 storms, and that's 600 composite storm event storms in this data set. And it's like 49,000 records in Excel. And once it gets past about 100, I'm out. I need programmers. So my colleagues at Ecology helped analyze this, and it's been fantastic. And what I can say about this compiled data set is, despite it being from the largest communities, because it is by land use, I think anybody in Western Washington can use this data set and have a baseline assessment of what stormwater quality is like. You know, the low density residential in Clark County isn't probably going to be that different from low density residential in Whatcom County. So I think you can gain information from this data set. I just really want to make sure you guys know about it because it'll be coming out next month. So this is a very robust data set. Being compositor samples, these are very representative of storm events. They looked at a lot of parameters. This is very, very expensive. They put out a tremendous effort to gather this data. The statistical analyses that we used, we consulted with HealthCell because a lot of these parameters don't have normal distributions. We needed non-parametric methods. The 15 to 18 labs that ended up being used to analyze this data all gave different reporting limits. We needed statistical tools that could handle this data set. So we do feel like we haven't introduced any bias by making assumptions about the concentrations of non-detects or the distribution of the data. The results are presented in this report, and there will be a website as overall, like if you can just get an overall sense of what total pHs are, but you can also get a sense of what total pHs are by land use and by season. And the best thing is, this is our data. This is our stormwater data. This isn't the NERP study. This isn't San Francisco Bay. This is Western Washington stormwater. And so I encourage you to use it. Oh, as I was alluding to, we had to make some statistical decisions here. There were a lot of non-detects for a lot of the organic parameters because in stormwater, depending on how big the drainage basin is, it may be a rather weathered sample. A lot of the organics may have volatilized, or they just may have broken down by the time they were sampled. Or maybe they weren't easy to detect anyway. So we had non-detects in the data set, and we decided to divide the data up into cases, kind of like my A, B, and C students, right? Where if we had less than 50% of the data was a non-detect, but less than 50 observations, we would use these various techniques. Most of these techniques actually are non-parametric, and they don't make an assumption about the value of the non-detect. Oh no, I have 5 minutes. They basically use its rank, and so they're purposefully included. So besides crunching numbers, we compared to the national data sets and a local study that was concurrent called the Toxics Loading Study, where they looked at storm loads from rivers. And that's really useful information because it gives us a sense of what the stormwater load in a river might be, whereas this is the outfall. So we did a comparison, a figure to compare against that. So we have the 1980s NERP study, the 1999 NASDAQ database, and our results are the x-axis. So what you can see are these are multiples. So for example, NERP in the 80s found that lead was 20 times higher in stormwater than what we were finding. Maybe that's because we've taken lead out of gasoline, right? But this Puget Sound Toxics Loading Study that has looked at a lot of the organics, for example, they were estimating pHs between 10 and 30 times lower was their stormwater estimate. So we can see the outfalls may be discharging higher concentrations. That makes sense. They're direct runoff. They're not necessarily diluted in the rivers yet. One of the things that I'll just point out on this graph right here is that dissolved arsenic is likely a geological source in our area, and so the rivers probably do have a higher concentration than stormwater. And the same or not the same, but nitrate is a dissolved. The nitrate is a dissolved nitrogen form. It is likely also not a source for stormwater. It's likely more coming from groundwater sources or fertilizers in the river basins, and not a heavy stormwater contaminant. Also, for context, we compared to criteria. These outfall weren't intended for compliance. This data set isn't intended for compliance, but we want to know what parameters are important. And it looks like that 50% of the 600 storm samples for dissolved copper tended to exceeded aquatic life criteria, and 58% for acute and then chronic criteria. You can see that it's largely to the metals and some PCBs that exceed criteria. We also compared the sediment values to the proposed freshwater sediment standards, and we can see that in particular 82% of the samples would exceed for bis-2-ethylhexyl phthalate and other organics. Metals exceeded 1% to 18% of the time for lead. And so basically we have a bunch of key points in this report and that we're making. We can really classify stormwater by the land use that it might be running off of, and we can begin to divide it, and in a way we might be able to orient our BMPs and our strategies for housekeeping or treatment towards the various land uses on how to control stormwater delivery. So some of the key results here are that metals are the most likely to exceed in stormwater. Commercial and industrial areas deliver the highest concentrations, and it looked like between seasons, metals tended to kind of have a buildup, whereas this is a bit of a seasonal first flush thing where the October through fall storms tended to be higher. I won't show you graphs because I don't have time. The organics, interestingly, didn't really have a buildup signature, and maybe that suggests that their sources are more continuous, such as, we're learning about PCBs in paints or caulking, and phthalates are from, all plastics everywhere, PHs, combustion products, but we did find them in all samples. They're very ubiquitous. And nutrients, ammonia didn't exceed any criteria for these stormwater outfall. Dry seasons were higher, dry season storms events were higher. And in particular here, I'm kind of starring that the total nutrients, so like particulate bound nutrients, were higher in commercial and industrial areas, but the dissolved nutrients were higher from residential areas. And in summary, basically, this is out there now. Give me 2 or 3 weeks, but it's out there and it's really robust. It's our stormwater data, and I really want you guys to know about it and use it. I think it fills a data gap. In particular, modelers, I think, should pay attention to this data, and we can focus our efforts on stormwater treatment and management, kind of based on some of this. So I'm hoping people grab a hold and run with it. Oh, my last 2 slides. The new permit, we're shifting from outfall monitoring to receiving water monitoring. We wanted to begin to understand the effects of stormwater in urban areas. On the receiving water, we have a streams monitoring program, and we have a marine nearshore, and we will have a couple sites in the Bellingham area, and this monitoring will be happening 2015 to 2017. So there's 6 small stream sites, and there's 2 Bellingham Bay sites, candidate sites, that we'll be monitoring. And this design is basically an inside an urban area and outside of an urban area, and that way we can begin to compare the impacts going on in those areas. So yeah, that's it. Look for links on the S8D. It was called Special Section S8D Monitoring. You can contact me directly. I'll help point you to the link. And we're going to make the data, the data's available. We'll give you a CSV file. Have fun.
Okay, thank you very much, Brandy, Jean, and Valerie. We have time for 2 short questions. We're making time for 2 short questions. Can we have the microphone? There's a gentleman here in the front.
Question for Randy. When you had the composite samplers out there, were you able to collect any discrete samples from the ascending hydrograph?
Is this on? They weren't required to, and some of the municipalities may have of their own interest, but that wouldn't necessarily been submitted under this permit requirement, and I didn't analyze it that way. Yeah. That's a lot of information.
PAHs in the livers of bottom feeders. Does anybody have any insight into what's going on there? Crabbing's been wonderful, but the bottom feeders apparently are down, and that's apparently the reason, because they're not feeding on the young crabs.
Yes, we have had some discussions with Jim West of the Washington Department of Fish and Wildlife. We've done a joint survey with him where he's looking for PAHs in the sediments in areas where they are finding PAH effects in some of the eggs of some of the fish, as well as in we co-sample some of these same areas, our long-term stations for both sediments and fish. So we have established that there are likely links between PAHs in the sediments and PAHs in the English sole, for example.
Okay, thank you very much. Can we give the speakers a hand again? Thank you for attending this session.
You've been watching a presentation from the State of the Bay Symposium held in January 2015 in Bellingham, Washington. If you'd like to see the other 6 presentations from this symposium, please visit the City of Bellingham's YouTube site, www.youtube.com/cityofbehamwa.